Hi, everyone. Welcome. My name is Emilia Huerta Sanchez, and Mark Broom and I co-organized the early series, the Early Career Research Series, which is part of the hybrid thematic program on modeling and theory in population biology. And of course, all of this is made possible by the Banff International Research Station. And so just before I introduce the speakers, I want to remind you that there's an event next Wednesday. It's going to be a mini symposium, 3 talks. And so that looks really exciting. So please join us for that. And so today we have 2 speakers, which I'm delighted to introduce. First, we will hear from Alex Stein, who is at Queen Mary University of London. And after that, we're going to listen to Maria Kleshnina, who is at Queensland University of Technology in Australia. And for her, it is 4 a.m. in the morning. So we really appreciate that you are presenting today. And so with that, Alex, the floor is yours.
Thank you very much. Okay, so you can see my slides, correct?
Yes, we can see them.
Perfect. Okay, so thank you very much for the invitation to Mark Broom and Emilia Huerta Sanchez. Yes, so my name is Alexander Stein. I'm a PhD candidate based at the Barts Cancer Institute, so Queen Mary University in London, and I'm supervised by Benjamin Werner. And I will talk about the mathematical analysis of the mutational landscape in cancer before and after treatment. So for those unfamiliar with cancer, so we think of cancer as an evolutionary disease that arises from healthy cells. And as part of the aging process, healthy cells in the human body are continuously replaced by new cells. And during cell divisions, they accumulate mutations. And some of those mutations will be cancer drivers. And eventually, cells divide uncontrollably, leading to what we know then as the cancer. But once the cancer outgrowth starts, so during cancer progression, we still have like an ongoing evolutionary process. As the cancer grows, more mutations will be accumulated, majority of which will be neutral and remain subclonal. And this will result in what is known as the genetic intratumor heterogeneity, which is widely observed in sequencing data in the past 10 years in particular. So with the advances of sequencing methods, cancer researchers started to borrow methods also from population genetics. And in particular, the site frequency spectrum obtained plenty of attention, which was, I think, first introduced by Fisher in 1930. But now, how do cancer research today use the site frequency spectrum? Well, first, we need to note that there is an observation problem. So we observe in cancer at the time of detection, but we do not know how the cancer has evolved before that, and we cannot really look into it. And so it was suggested as a solution to this problem to use neutral mutations as barcodes. They are accumulated over time and they leave traces in the sequencing data from which we can then infer the evolutionary history of the cancer. So in particular, there's a simple result for the exponentially growing population, where the site frequency spectrum can be shown to have like a typical 1/k² tail. And I will explain this in a bit more detail a few slides later. And these results are then usually fitted to the sequencing data at the time of detection, and we can make inferences. So this is an example. This is like the site frequency spectrum of a cancer. We see also that there's like quite some sequencing noise, in particular for the low and the high frequencies. But without going into too much detail, at least in the intermediate range, one can show that there's like a very good fit between the model predictions and the sequencing data. So this has actually led to a series of papers in cancer research. So it has, for example, led to this Nature Genetics paper here, where they tried to identify neutral evolution in cancers. So this was the 2 figures that I showed before. And it has then also be advanced to measure also or quantify the subclonal selection. So essentially, they just infer the selection coefficient of an arising subclone in cancer. And it has also been used to improve the phylogenetic tree construction. So these papers, they all have in common that they usually look at the sequencing data at the time of detection, and they want to make then an inference of the evolution during cancer progression. It has then also been used to study healthy tissues. So here they had looked at clonal hematopoiesis. So hematopoiesis, this is the formation of blood. But this is also like these two studies looked at the epidermis, so skin of an eye, where they also find like clonal expansions. This was also motivated from cancer point of view because we want to look at abnormal growth already before the cancer state. So I would call this like that they study the evolution of cancer initiation and they sequence healthy tissues. What has received very little attention so far is genetic patterns and the analysis of sequencing data after treatment, although we still have like ongoing treatment resistance very often and further problems. So this is where I want to come in, starting from a theoretical point. To study this, I use a birth-death process with mutations. It's a quite common model in cancer research. And it starts with a stochastic growth. So each cell has like a birth rate B to divide and a death rate D to die. And then in the second layer, we add mutations on top. So we say we couple the mutations to divisions. So for each division, each daughter cell has like obtains like mu1 or mu2 mutations, where mu follows like a general Poisson distribution, and we think that they are independent of each other. And if we propagate this process like forward in time, we will obtain this phylogenetic tree, where we, of course, at the end only observe the cells that survive. And so then we also want to have the aspect of treatment. So, and to do this, we divide our time into two phases. The first, during phase 1, we have like birth rate B1 and death rate D1, which are constant and leading to this average exponential growth up to this detection size ND at the detection time TD. And then we think that we initiate treatment, which will change the environment and thus also the birth and death rates. And we will have like a population size NF, F for final, and time TF. Now there are like three thinkable, qualitatively different scenarios that can happen. The treatment is effective and we have a decreasing population. It can maybe also stay approximately constant, or maybe treatment is not effective and then we will have a continued increase. In this model, we have like three key assumptions, which is first, we assume that birth and death rates have an exponential rating time, such that we have a Markovian property, and which makes the math a bit easier. Second, we assume each mutation to be unique, which is usually referred to as infinite sites or infinite alleles models. And we assume that mutations have no effect on birth and death rates, and in this sense, consider Newton mutations. And so we, at the end, look at the population, and then we want to, on the population level, we make sequencing, and we want to infer certain points. So we look at summary statistics of the mutational landscape, because yeah, I want to analyze the mutational landscape, right? So the first summary statistic we want to look at is the site frequency spectrum, as mentioned before, which is a quite well-known. So the site frequency spectrums partitions mutations according to their abundance in the population. In other words, we define here these objects Sk, which is the number of mutations that occur in K cells. So in our example population on the left side of 6 cells with mutations A, B, C, D, F, G, we would look, for example, like at mutation A, ask how often does it occur? It occurs 3 times, so we put this into the table. And then similar for B, C, D, E, F, G. And at the end, we want to look, for example, at S1, so how many mutations occur exactly once? And now we have D, E, F, G, which is 4, and we will end up with S1 equals 4, and then S2, 2, and S3, 1. So this is our first statistic we want to look at. Second, we want to look then, which is closely related to the site frequency spectrum, but then also has like a biological meaning with respect to treatment resistance, which is, we want to look at the total mutational burden, which we define here as the number of unique mutations. So in the above examples, the number of unique mutations is just A, B, C, D, E, F, G, which is 7. And eventually, and this has received a little less attention so far because it also comes with some difficulties of single cell sequencing, but it makes slowly its first steps. So we want to look at what we call the single cell mutational burden distribution. And as the name suggests, we count the number of mutations that come in a single cell. So we define this object mj, which is the number of cells that occur in j mutations. So in the left population, in this example, in this illustration, we have like one cell which occurs in which has only one mutation, and the rest of the 5 cells all have 2 mutations. Thus, we have M1 equals 1 and M2 equals 5. Okay, then now this is our model. These are like our summary statistics that we want to study. Now let's start with the first one, which is the site frequency spectrum. It may be noteworthy to say that each point in the site frequency spectrum is a random number in itself. So we deal actually with random distributions, and we want to focus most of the talk here like on the expectation of this distribution. And we start off with what's happening at the time of detection, shown here like in the right top corner again. And for this, we borrow like first methods from previously introduced by Otsuki and Gunnarson in 2017 and 21. And we compute the site frequency spectrum at the time of detection via this integral. So essentially what this integral does here, in short, is that we count the number of mutations that are generated at time t in this infinitesimal time interval t to t plus dt. So we have like an expected population size e to this exponential here. Each of these cells will divide with at rate b1, and will generate 2 cells with each have like on average m mutations. This is how many mutations we will generate in this time step, or d times dt. And then we want to condition those to grow to size k. And I think this is where the magic essentially happens. Then we need these probability mass function of the birth-death process, which are a little bit, they can be easy, but can also get quite complicated in most general case. But so we want this probability of a single cell to grow to size k in the remaining time. So if it's born at time t, the mutation, it has still time td minus t to survive and grow to size k. And eventually we just build the integral to sum over all infinitesimal time steps in our time interval of interest. So we can plug in our probability distribution and can solve it, and we can transform the integral then into this infinite sum here. A little bit more readable now is like maybe it's not so complicated, but a bit more easier than like maybe these limits, which then also have like an interesting limit meaning, which is first for large k. So for large clones, we will see that we have like this 1 over k squared, which is like this power law tail that I just talked about before. And another interesting limit is if we assume that the death rate goes towards the birth rate. In this case, we will have like a 1 over k power law, which is a typical characteristic of constant populations and has also been found previously for the constant size Moran process and White-Fisher process. And of course, we can also like compare this to simulation data. And so here the orange dotted line is the prediction, and the simulations, like there's a solid line which is a bit hidden between the dots. The dots is a single simulation. We average over many, and we find a very good agreement. So now we're also ready to look at the site frequency spectrum after treatment. For this, we separate between mutations that are pre-existing to treatment, and these are namely the ones that happen here during phase 1 and then just need to survive the phase 2. And then second, we also consider the mutations that are newly emerging. So mutations that are newly generated, survive, and grow to a particular size. And for the first one, we essentially start with sample from we take the result from the exponential growth phase, which gives us the site frequency spectrum at the time of detection, and then sample using the probability mass function of this birth-death process. And which is then like, so we have sk prime, and we want to know that all these clones of size k prime grow to size k in the time tf of treatment. And we sum them over all over the possibilities. And similar, like for the newly emerging mutations, we can actually follow a very similar approach to Gunnarson and Otsuki for the exponential growth. So we write again this integral, with the only difference being like this growth function now, which is not exponential growth starting from a single cell, but it starts like from the from the population size at detection, and then has like these 3 scenarios. And in total, we will have like that the total site frequency spectrum will be just the addition, like it will just be the sum of the contribution of those two. Looking at the first case, the decreasing population. So in general, we find that there's like a good agreement between our simulation results with like our analytic predictions, which is nice because we make also some approximations for the probability, for the most general probability functions, particular for like this pre-existing mutations. And there's like a general trend that large clones will have emerged during phase 1, which means that orange line is like going to make up the total set frequency spectrum here later on, and newly emerging clones are like rather restricted to small sizes, which is quite intuitive and makes sense. And we will see the same pattern also like in the constant and the increasing population. An interesting bit maybe in the decreasing population that we also find analytically is that in the limit that where the birth rates can be neglected, so they go to 0, which is actually reasonable also for cancers or for cancer treatment, if treatment usually happens at much faster time scale as like the cancer growth. And then for large enough K, we will still have like this 1/K tail of the set frequency spectrum. Okay, then next to the constant population, and I find here the results most interesting, actually. So we find like, again, like our approximation of the probability mass function gets a little bit off. Here we use, because it's not exactly known and we need to invert the probability generating function. So we use a saddle point approximation method. But so it's going to be off a little bit in the low frequencies, but for the higher frequencies, we see a really good fit. And in particular, also the newly emerging mutations have like this really simple form here. So just 2mn, and then this bt over bt plus 1 to the power of k, 1/k. This goes to this 1/k as time goes to infinity. So this is this typical characteristic power law of constant population sizes, at least at equilibrium. And yeah, I see like this like as a small extension of this result. And yes, so for large frequencies, we see like that also like the total set frequency spectrum is quite well predicted with these analytic predictions. And eventually, just for the completeness, also the continued growth case, the continued increase. So there are no actually surprises. Again, we find a good agreement between simulations and predictions. So now coming to the total mutational burden, which could be derived directly actually from the set frequency spectrum by summing of it, but because the integrals are already quite complicated, sometimes it's easier to derive them with a similar approach. And one can use some not so rigorous arguments to argue that and connect it to the tree and find that the total mutational burden B will be like a random sum. And then we can argue that both of them, like that the number over which we sum will be like both will be Poisson distributed, and then we will have like a compound Poisson process. It's not completely strict, in particular because of correlations, but we will find like that in general, at least in certain limits, we will have like a quite good fit to simulation data with this. And then maybe more interesting, the total mutation burden after treatment, we make again the same split that we look at mutations that are occurring before treatment and the one that occurring during treatment. So this is pre-existing mutations, newly emerging mutations, and some overdose. And yeah, so here first for the decreasing population, an interesting bit is here maybe that the total mutational burden after treatment is high compared to the expected population, compared to the total mutational burden with a comparable size that went straight from a single cell to this particular population size. So this is the black dashed line. And we find also like quite familiar or like a quite comfortable analytic result, in particular for the newly emerging mutations. The pre-existing mutations will still be like a rather complicated sum, but yes. Constant populations, an interesting bit like a dynamic is that the newly emerging mutations are quickly dominating. So we have like that this expectation of B2 will be much bigger than B1 after like a short amount of time. And we find that actually the newly emerging mutations are increasing logarithmically with time. So here this is essentially a logarithmic curve. And then we have the total mutational burden. I haven't said it. The dots is like simulation results. The line is our analytic results. So again, we see quite nice predictions here. And eventually, again, the continued growth case, we see, again, the newly emerging mutations have a very similar formula as like for the decreasing one. This is because the analytics of the supercritical and subcritical branching process are quite similar. And but otherwise, there are no surprises, really. Okay, and now to my last topic, which is like the single cell mutational burden distribution. So I like to think in these trees usually. So what I did there is like that I linked the single cell mutational burden distribution, which I called MJ, and I want to link it to what I call the leaf depth distribution, or I found it then later on in the literature as generation distribution. It's just asking, like in a tree, it means like if I take a leaf, how many times do I need to divide until I go back to the progenitor, to the beginning, to the root? And similar, it's then also just identical with the number of in which generation this particular individual is. And careful counting, I don't want to go through all the steps, but we can relate this MJ to this GM, so the single cell mutational burden distribution, we can link it to this leaf depth distribution according to like counting over all the mutations that occur on the way. And this is the random number, we can take the expectation over it, which will then take a form like this. So here we have the expectation of the single cell mutational burden, and here the generation distribution. And yes, then there's something that surprised me a little bit, which is like my naive approach was that I look at a single cell at the end of the population, trace it back to and I had like time t. So considering a single living cell at the end, I thought that the average number of divisions that should have occurred should be BT, but in simulation, I found 2BT. And then I looked into the literature here, Samuels in 1971, and also like just recently, there was a really nice paper by David Cheek and Johnston, that this is like due to like what is called an inspection effect. And they show that like as the time goes to infinity, we will have like this 2BT indeed. And the explanation is that individuals that proliferate early by chance will have more offspring and so contribute to a larger amount for the generation average. And I also tried them myself, doing some calculations, in particular for the pure birth process. So these guys usually look at more general branching processes, and I restricted myself to this and found like also like a small correction of -2. So we have 2BT -2 approximately, which is then also agreeing very well with my simulations. So here, this is just like the average, which grows in general linear with time. And these are like the full distribution, usually at the end time point. Here, this is a time of detection, and these are like the 3 scenarios of treatment. Because I'm running out of time, I'll skip it a little bit. Yeah, so now, final slide, coming to my summary. What I showed you is like, what we did is like we derived analytic expressions for the expectations of the site frequency spectrum, the total mutational burden, and the single cell mutational burden distribution after treatment. We found new and simple analytic expressions for constant population sizes, but also like for all the other cases, it's just that they take a nice form in this case. We show that the typical power law tail of the site frequency spectrum is remained after treatment. And we also characterize the behavior of the total mutational burden, single cell mutational burden, and find a correction in this generation distribution. Biology, I think it needs to be, some more work needs to be done, and it needs to be connected to data, but potentially we have like that the patterns on the site frequency spectrum will help us understanding the treatment response. We have that the total mutational burden after treatment remains at a relatively high level, which comes with a higher chance of multi-drug resistance. And the total mutational burden in constant population is quickly dominated by newly mutations. And those mutations that would stop chromosomal instability may be useful. And I just mentioned this because I'm aware that like an Institute of Cancer Research in London has worked on such treatments. And for the single cell mutational burden, maybe my message would be just be careful when inferring the number of generations because there's an inspection bias. And at this point, yeah, I just want to thanks to my team in London, led by Benjamin Werner. Also thanks to my second supervisor, Katarina Stankova and her team. And then also just thanks to my funder, which is my Career Program of the EU that also comes with a great network of researchers. Thank you very much for listening, and I'm open for questions.
Thank you, Alex. That was great. Very good talk. Does anyone have questions? Please start. Dave, Dave, and then John.
Hi, thanks for the really nice talk. I guess my question was thinking, connecting back to the biology a little more, which is essentially, do we have any idea about like if some of these mutations can, in a sense, I guess like promote more tumor growth and then essentially then act as like a modifier of mutation rate. So then you have, because of you carry that mutation, you'll then carry on more mutations. And so like how you treated just one kind of mutation rate throughout time, like I guess like in the standard coalescent, like I guess I don't know a lot about cancer in general. And so, yeah.
Yeah, I mean, like definitely we measure cancers the whole time, and or not we, but like people measure cancers like the whole time, and they find different mutation rates, and there is no real argument to assume that mutation rate should be constant over time. We think that it is, and we assume it for our model. If it's the real case, I don't know. Likely
Thank you.
For some cancers, but not for all. There are mutations that alter the mutation rate in short. Yes.
John?
Hey, thanks for a nice talk. I had a question about an assumption I think you were making, and sort of implicitly that you could that your analytical results really were for the entire population, not for a sample. Is that right?
Yeah, that's correct.
Some of the things that you were talking about might be more difficult, depending on how many cells you can actually sample and sequence.
Right.
More difficult to see and discern all of those details.
Yes. Yeah, no, I agree. So I usually look for rather strong effects that I hope survive sequencing noise. That's usually
how I work. Not so much noise as sampling error. So if you took a sample of size 2, then you only have one site frequency class.
Mm-hmm.
And if you have 10, then you have 9. And if you
say sequencing error, do you mean like sampling effects? Or
I mean sampling effects. I don't mean sequencing error. Not sequencing error at all. Sampling.
Right. Yeah. No. Yeah. I'm aware. Yes. Yeah. I mean, this is why people also like to use the coalescent by the end, right? But,
and what are the sample sizes that are available that you can use? In data.
Yeah, so I haven't worked with data yet. Like
okay.
I have like at the moment first approaches where I start with healthy tissues.
Perfect. Thanks.
But no, yeah.